Chapter 1.3, we're going to be going over the derivative and limits. So starting with what a derivative is, suppose we have a function f of x and we have a tangent line at every point on the curve of f of x. We saw in the previous section that we can actually find the formula that gives the slope of the curve at any point. So this slope formula is called the derivative of f of x. So the slope formula is called the derivative of f of x, and it is written like this, which we can read it as f prime or f prime of x, or the derivative of f of x. So essentially, for each value of x, f prime of x gives the slope of the curve y equals f of x. So the derivative of the function is the slope formula. So for example, if we have this curve right here, we have f of x, and we have this tangent line right here at the value for x. That means the slope of this tangent line is the derivative of the function at that point x. Okay, and then a couple other things. The process of computing f prime for a given function is called differentiation. So taking derivatives is called differentiations. And as we're going to see, some curves don't have tangent lines at every point, and we would say that at these points the derivative is not defined. So let's start with a couple examples of derivatives. So ones that we actually know the derivatives for without even doing any calculus are linear functions and constant functions. So linear functions we know are lines when we graph them. Linear functions have constant slopes. No matter what point we're looking at, no matter what interval we're looking at, the slope of a linear function is constant. That means the derivative of a linear function is that constant slope. So if we have f of x equals mx plus b, so this is slope-intercept form for the equation of a line, we know that the slope of this line, whatever these numbers represent, m and b, the slope is the m value. That means the derivative f prime of x equals whatever that m value is. So let's see this example here. We have find the derivative of f of x, which is 4x minus 7. So the derivative f prime of x equals the slope. The slope is 4, so that means the derivative is just 4. So no matter what point, what interval we're on, the derivative of this function is 4, meaning the slope at any point on this line is 4. Next one, we have constant functions. Constant functions are horizontal lines. We have to remember that they're in the form f of x equals b or y equals b, so it's just y equals a number, and that's a horizontal line. The derivative of a constant function is going to be 0. So f prime of x is 0 for any constant function. That means the slope is 0 no matter what point or what interval we're at for a constant function. So taking a look at this example, we have f of x equals 3. We want to know what's the derivative of this function. So the derivative f prime of x, we say, well, this is a constant function. It's f of x equals a number. And anytime that happens, the answer is always 0. The slope is just 0 for no matter what point we're at. Okay, so those are easy enough. Now let's make these a little bit harder and get to essentially one of our first rules here for finding derivatives. So this first rule is called the power rule, and it's going to help us find the derivative of power functions. So remember that a power function is the form f of x equals x to the n, where n is any number. So it's just x, the variable x, to some number, and that's what we call a power function. So the power rule lets us determine the derivative, and it says if f of x is the power function x to the n, then the derivative f prime of x is n times x to the n minus 1. So what this means is when we're given a power function, we're going to multiply the original exponent out front, and then the new exponent is going to be 1 less than the original one. And let's go ahead and see an example here. keep that on here. Okay, so calculate the derivative using the power rule. So let's go ahead and calculate the derivative of the first one. F of x is 3x. We should know that this is a linear function and the derivative is just 3 because that's the slope. But let's actually go ahead and rewrite this as 3x to the first, and let's apply the power rule. So the power rule says we bring down that out front to multiply it. So that's going to be f prime of x is 1 times 3x, and then we're going to subtract 1 from the original exponent, which is going to be 1 minus 1. So we're going to get, obviously we can get rid of that 1 out front. We're going to get 3x to the 0. Anything to the 0 power is 1. So that's going to be 3 times 1. So that gives us f prime of x, the derivative equals 3. Which once again we already knew because it was a linear function. So that's kind of like the drawn out explanation of it. Next one, we have f of x equals x squared. So for this one, we're going to calculate the derivative, f prime of x. And what we're going to do is we're going to take that exponent, bring it out front by multiplying it out front. So it's going to become 2x. We're going to subtract 1 from the exponent, so 2 minus 1 is the new exponent. And that's going to end up giving us f prime of x equals 2x to the first, which is just 2x. So the derivative of f of x equals x squared is just 2x. A couple more here. For example C, we have f of x is negative 5x cubed. So once again, these are all power functions, right? Because they're all just these single terms with exponents that are just real numbers, so they're power functions. So let's go ahead and take the derivative of this one. So we're going to bring down the exponent out front, which means we're multiplying it out front. And we're going to subtract 1. And we need to simplify that. So we're going to get f prime is 3 times negative 5, negative 15, x squared. We do not have to show this step right here. You can skip right to the answer if you can do it in your head. All right, and then next one here we have D, f of x is the square root of x. In order to do this, we have to know that the square root as an exponent is the same as x to the 1/2. Once we know that, we can go ahead and take the derivative. We bring down the 1/2 out front, multiply it out front, subtract 1/2, whoops, I put that backwards, 1/2 minus 1, the original exponent minus 1, and we have to simplify it. That's going to be 1/2 x to the negative 1/2, because 1/2 minus 1 is negative 1/2. And we can write it like this. That's technically fine, or we can write it like 1 over 2x to the positive 1/2. And just to kind of get a final answer here, that's the same thing as 1 over 2 radical x. So any of those are actually 100% accurate. All three forms there all mean the same thing. Next one, we have f of x equals 1 over x. 1 over x, we have to remember that 1 over x is the same as x to the negative 1. So a couple of these you can see just come down to remembering how to rewrite certain things. Now finding the derivative, we're going to bring down the exponent out front and subtract 1 from the exponent. So that's going to give us f prime of x equals negative x to the negative 2, which we can write as f prime of x equals negative 1 over x squared to make the exponent positive. And sorry for having it all clumped together here in my notes. Next one, we have f of x equals x to the 3/4. So f prime of x is going to be bring down the exponent out front, multiply it out front, subtract 1 from that exponent. Let me just move down this other one here. Subtract 1 from the exponent. We get 3/4 times x. 3/4 minus 1 is negative 1/4. And if you have to get common denominators for that on the side, okay, 3/4, it'd be 3/4 minus 4/4, which is negative 1/4. And we can leave it like that, or once again, we can make it positive by putting it in the denominator. So that would end up being 3 over 4x to the 1/4, or we can write it as 3 over 4 times the 4th root of x. So I personally like this one the best. However you want to write it is completely fine. I'm just going to circle this one. Okay, and I'm just going to space this down a little bit so we have some room here. There we go. Last one, f of x equals 2x to the 5th. And we have f prime of x equals, we're going to multiply the 5 out front, subtract 1 from the exponent, and that will give us the derivative is 10x to the 4th. Okay, so that is the power rule. Okay, and the next thing here, let's go over just some more ideas about the derivative and what it means, going over kind of a geometric meaning of the derivative. So in general, the derivative of a function, f of x, at a point x equals a, it's the slope of the graph at the point a comma f of a. And the slope of the graph at the point is the slope of the tangent line at the point. That means we have this geometric meaning down here that f prime of a is the slope of the graph at f of x at a comma f of a, which is the slope of the tangent line there. So pretty much exactly what we just said, but just more formally written out here. And just kind of a little side note, don't confuse f of a with f prime of a. F of a is the y-coordinate at a. F prime of a tells us that slope at x equals a. Okay, so two different things. Let's see an example here. For example, let's find the slope of the curve y equals 1 over x at 2 comma 1/2. Let's draw a rough sketch of this curve. So we should know 1 over x is a rational function. It's called the reciprocal function. If you plug in a bunch of x's and make an xy table and graph it, it would end up looking something like this. So the point 2 comma 1/2 would be, let's say, about right here. So if we're looking for the slope of the curve there, that means we're looking for the slope of this tangent line at that point. And the slope at that point, or the slope of the tangent line, equals f prime of 2, because that's the x value. So let's go ahead and find the derivative. Let's just call this function f of x, 1 over x. So taking the derivative now, let's rewrite this so it resembles a power function, x to the -1. We actually did this on the previous page, so I'm just going to write the answer here. It's -1 over x squared, or negative x to the -2. So if we want f prime of 2, all we have to do is plug it in the derivative. So plug it in, and we get -1 over 2 squared. So we get f prime of 2 equals -1/4. So that means the slope of the curve at that point is -1/4, which seems reasonable because what we drew over here, we know that's a negative slope because it's a decreasing line. So it seems like that slope of that tangent line at that point has the slope of -1/4. Okay, and now the next thing is the equation of the tangent line. So using the point a comma f of a and the slope that, using the fact that the slope is m equals f prime of a, so slope, just like we just did, is the derivative evaluated at the x-coordinate, we can find the equation of the tangent line. So here's the equation of the tangent line. Y minus f of a equals f prime of a times x minus a. Hopefully this looks familiar. This is just point slope form for the equation of a line. Same exact thing, but instead of y1, we have f of a. Instead of x1, we have a. And instead of m, we have f prime of a. So same exact thing, just using different notation here, using derivative notation also. So for this example, let's find an equation of the tangent line to the graph of f of x equals 1 over x at the point 2 comma 1/2. So as soon as you see that we're trying to find an equation of the tangent line, we should be writing down exactly what was just above. Y minus f of a equals f prime of a times x minus a. Or you can write down using the point slope form, y minus y1 equals m times x minus x1. And we need, same thing as last time, we need, I'll write it as a comma f of a. This is just x1, y1. That's given to us, 2 comma 1/2. And then we need f prime of a, which is going to be f prime of 2. So we actually, I believe we just found this, didn't we, on the previous page? Yeah, f prime of 2 for this function, we got negative 1/4. So I'm just going to cheat a little bit and put negative 1/4. And I'll put a little note saying see the previous page. You have to find that the same way we just found it. Once you have these three things, it's similar to what we've done before. We just plug everything in. That's going to be y minus 1/2 equals negative 1/4 times x minus 2. Since all it says is find the equation of a tangent line, we don't have to solve this for y and put it in slope-intercept form. We can just leave it in point-slope form, and that's technically fine. That's one form of the equation of the tangent line. Next one, let's find the point-slope equation of the tangent line to the graph of f of x, which is 1 over x squared, to x equals 2. So once again, equation of the tangent line, we should be saying y minus f of a equals f prime of a times x minus a. So we have to find a comma f of a. So we're given x is 2. So that's our a value is 2. This time we're not given y. We actually have to figure out what y is, and we have to do that by plugging it in the function. So f of 2, here's the function right here. That's going to be 1 over 2 squared, which is 1/4. So f of a is f of 2, which is 1/4. And lastly, we need f prime of a. So to find this, we need f prime of x. So let's go ahead and take this derivative. We'll do it right down here. F prime, let me rewrite f of x first. We know f of x is 1 over x squared. We can rewrite that as a power function as x to the negative 2. And let's go ahead and find the derivative. We bring down the exponent, multiply it out front, subtract 1 from the exponent. Negative 2 minus 1 is negative 3. And maybe let's just clean this up a little bit. Let's write this as negative 2 over x to the positive 3. Now when we're evaluating f prime of a, that's f prime of 2, all we have to do is plug in a 2 into this function. So it's negative 2 over 2 cubed, which is negative 2 over 8, which is negative 1/4. So that is our f prime of 2, our f prime of a in this case. So once we have those three things, so we go ahead and plug everything in. So it's going to be y minus f of a, which is 1/4, equals f prime of a, which is negative 1/4, times x minus 2. And this one actually is asking for point slope form, which is good because then we're done. We just plug everything in. We don't have to solve for y, and we are done. So that is the equation of the tangent line to the graph at that point. So let's just draw a quick representation of what we actually did. It's good to be able to think of things graphically as well as algebraically. So here is the function y equals 1 over x squared, something like this. And if we have the point 2 comma 1/4, maybe that's, say, right here. So the tangent line at that point might look something like this. And we just found the equation of this line. Okay, so that is what we found for that equation. All right, now for just kind of a shift in notation, we've been using this notation f prime of x for a function f of x to show that it's the derivative. Another way we can do this is using this notation right here, d over dx. This is read as the derivative, so that's the d in the numerator. The derivative with respect to x is the dx in the denominator. Okay, so let's go ahead and determine the following here. Also, I just want to make a note that f prime of x, if we're using y, we could also just use y prime. That also works. Okay, let's determine the following. So we have d dx, and then we have x to the 6. So this means it wants the derivative of x to the 6 with respect to x. So it probably seems obvious. Obviously, we're doing it with respect to x, meaning x is our variable here, because that's all we're using, but we'll see a little later on that we'll have multiple variables in here. So taking the derivative here, that's just going to be power rule. That's going to be bring down the exponent out front, subtract 1 from it, and we're done. So d dx of x to the 6 is 6x to the 5th. Same thing for this next one. We have the derivative of x to the 5/3 with respect to x. So let's go ahead and bring down that 5/3. And then we're going to do 5/3 minus 1 in the new exponent. This is going to end up giving us 5/3 x to the, what's this going to be? I guess 2/3. And I'm just going to leave it just like that. So once again, just getting common denominators, that's 5/3 minus 3/3, because 1 is the same as 3/3. So yeah, 2/3. Okay. Okay, and just kind of another note here. When we have the derivative in the form y equals f of x, we can write dy dx as a symbol for the derivative f prime of x. So also dy dx equals f prime of x or equals y prime. So just know all three of these mean essentially the same exact thing. Okay, let's calculate the derivative. Y equals x to the 6. So obviously this is really repetitive. This is just showing change in notation. So if we want the derivative dy dx, we could have written it as y prime also. That's going to be 6x to the 5th using the power rule, and we are done. Okay, so just showing off our different notation here, nothing new. So now moving on to secant lines. So this is a really important concept that we're going to be working with for the next few chapters here, few sections. Let's say that we have a curve, and let's just say it looks something like this, and this curve is f of x, and let's say we have a point P on this curve. Let's let P be right here. This is point P, and we're going to say that its x coordinate is just x. It's just some, whatever x is, just some random x. The point here is that it's going to be a fixed point. P is not going to move at all. Okay, now let's choose a different point Q. Let's say that Q is over here. That's point Q. And we're going to say that it is horizontally h units to the right of x. So if this point right here is h units to the right of x, that means this point is x plus h. So that's because whatever this distance is h. We just let it be some distance to the right, h. Okay, so if we go ahead and connect these lines, and we connect them just like this, this line that's crossing through both of these points is called a secant line. So secant is a line that's cutting through 2 points. Okay, so if we wanted to calculate the slope between these points, we can calculate them because we know the slope formula is m is y2 minus y1 over x2 minus x1. But we don't have x2, y, or x1, y1, x2, y2. It's a little bit more complicated here for us. For this point, for the x plus h point Q has coordinates x plus h for its x coordinate, and then its y coordinate would be the function evaluated at that x coordinate. So it looks pretty confusing. And then for P, we said the x coordinate was x. That means the y coordinate is just whatever f of x is. Okay, once we have that, we can actually find the slope between them. We can say that the slope between them is y2 minus y1. So a difference in their y coordinates divided by the difference in their x coordinates, right? y2 minus y1 over x2 minus x1. So what actually happens here is that the x's in the denominator cancel off, and we are left with f of x plus h minus f of x, all divided by h. So this is actually something, that's very, very important. This is called the difference quotient. And that's going to be something that's very, very important for the last page in this section, as well as going forward. So what we're going to do is we're going to be moving point Q closer and closer to point P, and the secant line is going to be moving with it, and P is going to remain the same. So what's going to happen is that as Q gets closer and closer to P, H, the distance between them, is going to be approaching 0, right? If Q is approaching P, the distance between them is going to be approaching 0. What that means is that the secant line approaches the tangent line. And what that means is that this difference quotient approaches the derivative at that point, because the derivative represents the slope of the tangent line. So that's hopefully not too confusing, but let's click this link here and see a representation of this on a graph. Okay, so what we have here is the black dot would be point P, the red dot would be point Q, and you can see the secant line between them. Point Q, the red dot, is moving closer and closer to point P, and once it gets right on top of it, the distance is 0, and that is the tangent line at point P. So it's secant line all the way until the distance is converging to 0, and once it gets right on top of it, the secant line becomes the tangent line at point P. Okay, so hopefully conceptually that makes a little bit of sense here. So let's kind of summarize the process that we're going to be calculating f prime of x with. We're going to do it more formally in the next section. If we want to calculate f prime of x, and we don't want to use the power rule will work for this example that we're about to do. But what we're going to do for this one is we're going to start by writing the difference quotient out. So we're going to write f of x plus h minus f of x over h. And then what we're going to do is we're going to plug in f of x plus h and f of x, and then we're going to simplify it. And you'll see how we do that in a second. And then we're going to plug in a 0 into h. That value that we get is going to be, that function that we get that's left over is going to be f prime of x. So let's see, I think we only have one example because we'll be doing more of these in the next section. So let's use this above method to show that the derivative of f of x equals x squared is f prime equals 2x. So we know this based on the power rule, but let's do it the other way. So we have the difference quotient, f of x plus h minus f of x over h. And what we can do here is on the side, we can actually find f of x plus h. We're going to plug it in where there's an x, which is x plus h squared. And then we have to simplify this. X plus h squared is x plus h times x plus h. If we FOIL this out, we get x squared plus hx plus hx. I'll move that over a little bit. We get x squared plus hx plus hx plus h squared. The two middle terms combine. So f of x plus h becomes x squared plus 2hx plus h squared. So let's go ahead and substitute in now into the difference quotient. Instead of f of x plus h, we can rewrite x squared plus 2hx plus h squared, because that's what f of x plus h is. And then we have minus f of x. Well, f of x is right here. That's just minus x squared, and that's all over h. So now we need to simplify this. Simplifying this, we can recognize that the x squareds are going to cancel. Anytime you have a polynomial, that means the f of x over here on the right, the whole thing is going to end up canceling. So the x squareds cancel. We end up getting 2hx plus h squared. We clearly cannot plug in a 0 yet, right? Because we'll be dividing by 0 if we plug in it in for h. But we can factor out an h in the numerator and get h times 2x plus h over h. Now we see that an h cancels, and we get 2x plus h. So that's what it simplifies to. Based on the instructions above, we plug in 0 into h, so that becomes 2x plus 0. So 2x plus 0, which is obviously 2x. So this right here, what we actually just found, is the derivative of f of x equals x squared. We found it using this alternative definition, using the fact that a secant line becomes a tangent line as the distance between them goes to 0, as the h value goes to 0. Okay, so we'll continue on this idea more formally in the next section.